Hi there, good day. Today I'll be sharing a paper, Phonetic Enriched Text Representation for Chinese Sentiment Analysis with Reinforcement Learning. So the general idea of this paper is cognitive-inspired phonetic features in the Chinese language offers exceptional advantages to the conventional textual representation. And this has been proven effective for sentiment analysis tasks. So the outline of my sharing will start with two background knowledge of phonemic orthography and intonation variation. Then I'll be using these two to represent Chinese text. And then we have introduced the model design for sentiment analysis task. Then we'll present the results and analysis. So first thing first, what is phonemic orthography? So the orthography itself is essentially a system for writing a language in which the graphemes or the written symbols corresponds to its phonemes, which is a significant spoken sounds of the language. So typical examples with shallow languages are like Italian, Spanish, Finnish, and Hiragana and Katakana. Deep ones will include like Chinese, Hungarian, Arabic, and Hebrew. If you know any of these languages, so shallow means it is very easy to pronounce based on the given word, even if you don't know how to pronounce a word. But deep, it means it is very difficult to pronounce given the written words. And this phonetic channel provides complementary semantic cues to the textual channel. Is one example shown here. The Chinese sentence, I suppose tomorrow is a holiday. So the first and last Chinese characters, they appear the same in a textual form, but they were pronounced differently, meaning different meanings. The second characteristic of Chinese is the intonation. Here we are talking about the Mandarin. So for the typical Mandarin, each Chinese character will have 5 different tones. And as is example shown here in the first row, the 2 tones will essentially mean different meanings. It could mean empty or free, which 2 of them are neutral sentiment plurality. Where for the second row, the character, as we also show in the previous slide, has 2 intonations, which means fake as well as holiday, and will result in different sentiment polarity. It could be neutral, negative for the fake, and neutral for the holiday. For the last word, it could mean delicious, which is a positive word, and gluttonous for the negative one. As we showed in the previous slide, the same sentence, the first and last character, because they pronounce differently with different intonations, and they will mean different things. Next to the previous 2 features, we came up with the representation for the phonetic features. And we have 2 variants. The first one is extracted from audio. Essentially, we connect the character audio clip and extract audio features out of it. The second type is learned from pinyin corpus. Pinyin is the romanization of the Chinese character pronunciation. So we firstly convert the textual corpus to pinyin corpus, and we learn the pinyin embeddings. So examples are like for the same sentence, suppose tomorrow is a holiday. So the pinyin, as you will see, each of the Chinese character will have 1 pinyin with tones. And for the 2 features, EX, as well as for the P, EX0 is 1 subvariant, which we eliminate the intonations. And EX04 is essentially the pinyin with different tones. And the PO is pinyin without the intonations. And the PW are the pinyins with the intonations. In order to use the intonation variation, so we came up with the disambiguate intonation for sentiment analysis, or DISA network. So this is essentially a reinforcement learning network. So we map the 5 different intonations to 5 actions. Here denotes 0 to 4. As different indexes. So what is essentially be used in our framework is, for example, for the 1 Chinese character A, it will have 5 different tones, and each tone will map to 1 index. For each of the index, it will have 3 components. The yellow box means textual embeddings, and the red ones were the phonetic features, which are the combination of the previous two features we introduced. And the green one are the visual features. So a combination of the three will form up the features for each intonation of this Chinese character. Next, I'll introduce the model design. So it is the DISA network, which is the actor-critic network. For the actor network, so we have one Chinese sentence represented by C. C is a Chinese character. Then we look up its pinyin without tones. The next step is for each of the pinyin, we're trying to select one out of its 5 intonations. And each of the intonations will look up for its feature embeddings, which we have pre-stored. And these features will send to an LSTM for sequence learning. The hidden states for each of the time step will send to the next time step for in the actor network to select one out of the 5 intonations. And the final state will send to a softmax for the sentiment polarity prediction. And the loss of the sentiment polarity will be used as a delayed reward to tune the actor network. So the state, action, and reward were given here. The objective of the actor network is to maximize the selection of the correct action or intonations for each pinyin, whereas for the critic objective is to increase the accuracy of the sentiment polarity. For the evaluations, we're having various data sets. Some of them are microblocks and others were reviews from different domains. As for the baselines, we have SOTA representation from the textual embeddings as well as visual embeddings and a bunch of self-variants of the DISA network. For the unimodal comparison, we compare different modalities of textual representation, visual, as well as phonetics. As you will see, for unimodality, glove performs the best as expected, and phonetic features alone cannot beat the textual embeddings. That's why we came up with a multimodal comparison. So phonetic features consistently improve performances when fused with other modalities, and we could observe that textual plus phonetic features achieve the best performances. However, to our surprise, we can observe that T plus P plus V does not perform the best. And we conjecture that it is a trade-off between non-redundant information and increase of training parameters. It's one example shown here. 2 Chinese characters, they pronounce essentially the same. However, the visual features of the 2 were different. So they encode different semantics. So that pretty much covered the information which has been carried by the phonetics, whereas phonetic features pretty much increase the training difficulty. The next evaluation is a cross-domain validation, where you essentially train the model on one dataset and test on the other datasets. You will see that the DISA network with T and P features perform the best, has the best cross-domain performances. We believe it is due to the common tokens shared by the training and test datasets. That's why we plot the ratio of the intensity between the 2 data sets on the figure on the right. So the phonetic features provide better generalizability than the textual embeddings alone. The summary: deep phonemic orthography and intonation variation are special to Chinese. And the phonetic channel offers complementary semantic cues to the textual representation. The fusion of phonetic and textual representation can improve Chinese sentiment analysis, and phonetics can be applied in other natural language processing tasks. That's all for the sharing. Thanks for watching, and hope to see you again.